Hello and welcome to another series of credit risk modelling videos, and this time I'm going to be looking at decision trees and everything to do with them, from the very basic categorical ones to ones including values to using things like bagging, bootstrapping, all these different ways you can improve the use of data as well. I'm going to start at the most basic level with what exactly a decision tree is, how it works on just simple categorical data, because this really gives us the basis for how we can then move to more complicated decision trees and more complicated ways of fitting decision trees afterwards. So here we are, modelling credit risk using decision trees. And first, just an overview of what a decision tree actually is. So a decision tree is a structure which allows you to classify data. So there are ones which look at regression as well, but if you're looking at credit risk, you're really trying to classify stuff. You're trying to work out if a company is solvent or insolvent. So decision trees allow you to do that. They're classification tools, and they allow you to classify on any number of characteristics that you might have. They can be used on either categorical or continuous variables. So you can either have things where it is a straightforward yes/no answer, or a continuous variable where you have to work out a cut-off point, and then you have if it's greater than, go one way; if it's less than, go the other way. And there's a number of algorithms which are in place to construct the trees, because one of the key things about decision trees is the way that they are put together is not arbitrary. There are rules that you need to put in place to make sure that the decision tree that you come up with is the best way of the best roadmap you'll have for classifying the data. And as I said, there's a number of additional techniques out there as well, like boosting and bagging, which you might have heard of. And these are things that you can apply to, well, not just decision trees actually, but anything which is trying to categorize data can use these approaches to try to get the most out of that data. So I'll cover those right at the end of this short series. So first, a bit about decision tree structure. All decision trees start with a root node, which includes all of the potential candidates, everything that you're going to categorize. Then each decision that you make leads to either another decision or to a terminal node. So a decision node gives you another choice, and a terminal or a leaf node gives you with the result of all of the choices from following that particular route. You can also look at individual subsections of your decision tree, and these are known as subtrees, or sometimes known as branches as well, to keep the horticultural or arboreal theme going. And these start at a decision node and they end at terminal nodes. Other important concepts in decision trees, you've got parent nodes and child nodes. Parent nodes understandably lead to child nodes. When you've got a particular node and you split it into two or more subnodes, then that's called splitting. And if you do this, you need to have a choice of feature and a criterion to determine the split. So for categories, it's pretty straightforward, it's just yes or no. For continuous variables, it's a little bit more tricky because you need to work out, as I say, where that cutoff point comes. Now, when you've created a decision tree, you might want to try to cut it back to make it more manageable. And this is known as pruning. And it is a way of dealing with the fact that some of the information you might have might involve outliers which aren't particularly reliable. And also some of the subtrees might not give you great classification power, so they might not leave you much better off than you were before. So pruning allows you to take care of this and get to something which is a little bit more tidy and something which is just a little bit more efficient. So here's an example of a decision tree using categorical variables, and it's one built around breast cancer screening. I should say, the numbers here are based on real data. This isn't actually an example which is used to determine screening, but the numbers here, they're the right kind of order of magnitude based on UK data on breast cancer diagnoses. So this made-up model I've got here, it's it's designed to help you decide whether or not you want to screen someone for breast cancer. And the arbitrary criterion I've picked is that the probability of developing breast cancer in a given year is greater than 0.1%. So that should be ultimately what you want to do to decide whether you screen someone. If someone at the end of this process has a probability of greater than 0.1%, then you want to screen them. So the probability of diagnosis at each of the different points is shown. That's the number in the parentheses. And this is what we have so far. So you start off with all your data and you say, okay, well, first question, are they male or female? If they are male, or I should say, are they female? Yes or no. So if they're not female, so they're male, then the probability of breast cancer diagnosis is 0.001%. So that is so small that no further sub-classification is going to get you much higher. So do not screen in that case. If it's yes, got a 0.189% chance. But although that is greater than 0.1%, you don't want to screen every single woman if you can possibly help it. So it's worth just asking a few more questions. The next question will be, well, are they over 50? And I know this is actually a continuous variable rather than categorical. As it happens, you can treat it as categorical because the data on a more granular level just isn't easily available, whereas under and over 50 is broadly available. So treat it as a category. Are they over 50? If they are over 50, then the probability of a diagnosis goes up to 0.431%, so we should screen all women over 50. If they're under 50, so the answer to that question is no, then it drops to 0.063%. So on the face of it, you might not want to screen them. But you could ask a further question, and that question could be, do you have any close relatives with breast cancer? Because if the answer is yes, then that probability rises again to 0.703, in which case you want to screen them. If they don't have any close relatives, then it goes to 0.047%, so you wouldn't screen them. So this is a fairly simple example, but it shows you how a decision tree could work in practice in terms of categories. Now, of course, you might want to know, well, why do you ask these questions, and also why do you ask them in this order? Is this the best order that you can ask them? And a way of answering this is to use an algorithm. And an algorithm, or one of the first algorithms which works well with categories, is called ID3, the Iterative Dichotomizer 3, which was clearly much better than the Iterative Dichotomizer 2 or even 1. And this is a decision tree algorithm. And it works with attribution selection measures, ASMs, to divide the data. And a good ASM is one which gives you the biggest reduction in impurity in a subset. So impurity means, in a subset, means you've got a greater mix between two different categories. The purer the subset is, the more it is dominated by a single category. So in this case, either developing or not developing breast cancer, or rather having or not having a breast cancer diagnosis. Now, one measure of the reduction in impurity is information gain, and we'll see what that is, how we calculate that, how it's defined a little bit later on. Now this algorithm, like pretty much all algorithms out there for decision trees, is known as a greedy algorithm. And what this means is that it makes the decisions at each particular node, and at each particular node it makes the best decision that it can with the information at that node. And having made that decision, it doesn't then backtrack to see whether a better decision could have been made if the previous choice was better, and it doesn't use that decision again in further analysis. So it only looks at the locally optimal decisions. So there's a chance that what you might end up with is not a globally optimal solution, but it does work very well, and it does work pretty efficiently. So the first stage in the ID3 algorithm, you define your data set as S, so this is all of your data, your whole population in this case. At least it is at the start, because as you move through the different nodes, what counts as S changes. So it would start in our example as being the whole population. Then the next node it will be all women would be the next, would constitute S. Now for each data set S, you want to calculate the entropy, which we've denoted H. And if you've got a number of classes X which belong to a set of classes capital X, which might be, say, women and men might be two separate classes, then your entropy is calculated by summing over all those classes X, Px, so the proportion that make up that class X, times log to the base 2 of Px. You sum all those and then take the negative of that. So Px is the proportion of the elements of that set S which sit in class X. And Px has to be not equal to 0, because, well, actually it has to be greater than 0, because you can't take a log of 0 or a negative number. So you split the data set using attribute A. And attribute A is the attribute which gives you the highest information gain. So what is information gain? It is essentially the how much you can improve the entropy number by. So HS we calculated as the entropy. What we then do is we look at the entropy within each of the different classes and multiply that by the proportion of those classes and then deduct that from the initial entropy. So that shows you how much better you're getting with a particular classification measure. And T is the class of subsets which are obtained by dividing S by attribute A. And HC is the entropy of the subset little t. So you do this for all possible attributes. And the choice you make is the attribute which has the highest information gain, so the one which gives you the best improvement in classification, that becomes your first node. Then, so you make a decision tree node using that attribute, and then you repeat this on further subsets with the remaining attributes. And you continue, well, you can kind of continue until your entropy equals 0, which means all elements are in the same class, or at least until you can't get any further improvements in information gain or any reliable ones for the work taken. So here's an example using the data that we had before. So breast cancer screening, you've got 3 potential attributes: age band, sex, and close relative status. So the first thing you want to do is you want to calculate the entropy for that whole set. So this is your starting point of the entire population, based on the 1-year incidence of breast cancer, 1-year diagnosis probability of breast cancer. So you've got 2 classes, being diagnosed and not being diagnosed. And the proportion of the population being diagnosed with breast cancer each year is PX1, which is 0.0975%. So the proportion not being diagnosed, PX2, is 1 minus this. So HS is minus 0.000975 times log to the base 2 of that, plus then minus 0.000975 times log of 2, 1 minus 0.000975, which gives you this initial entropy number, 0.011161. Next, we want to try and calculate the information gain from the full data set. So we've got the proportions who are diagnosed in each data set for the over 50s and for the under 50s, for males and for females, for those with and without a close relative diagnosis. So that's PX1 and PX2. We can calculate the entropy for each of those individual groups, and also the proportion that we have in each of those groups. And that allows us to calculate H of S given A, and therefore the information gain. So what this suggests is the greatest information gain, which is the second number down in the final column, so 0.000881. This is the biggest information gain, and it is for sex. So splitting between men and women is the best first move that you can have. So if we then start with that, and we then move to the female data set, we know what the entropy is for that. We can calculate that. Indeed we did calculate it in the previous step. And then for just women, we look at women greater than or less than 50, women with or without a close relative diagnosis, and we do exactly the same calculations again. And this shows us again that age is the next best classifier. It has the highest information gain, 0000953. So the next node is age, and so on and so forth. And what you find is you end up with a decision tree which is like the one that we calculated initially. Now, there could be a number of other factors that you could consider. I mean, things like lifestyle, tobacco and alcohol, obesity, diet, ethnicity, genetic markers. There's a whole load of other things that you could take into account if you were using this to come up with a screening program. But the key things are the availability of the data for actually being able to perform such a fit, how reliable that data is, and also whether you've got something which is a category or a value. So, for example, alcohol. Are you going to have drinking and not drinking? Are you going to have drinking more than a particular number of units? Are you going to actually have the number of units drunk per week as a factor? I mean, that would be the most reliable, but it's also probably the least available. So you've got all those sorts of things to consider as well. So let's leave it there for now, and next time we'll start looking at continuous data and how we deal with that additional level of complexity. But hopefully that's given you a useful introduction on how decision trees at the very highest level work.